Hi dear students, this is the lecture series on topology second with course code MTH802. Today we are going to discuss some properties of Housdorff spaces. Properties of Hausdorff spaces. Hausdorff spaces, or we can say T2 space. Okay. So let's we have first property that's which is in the form of theorem. Let us state this theorem. If X is a Hausdorff space, if X is a Hausdorff space, if X is a Hausdorff space and this point X, it belongs to X, and C is a compact subset of X. C is a compact subset of X such that X is not in C. Then X and C can be separated by disjoint neighborhoods, or you can say disjoint open sets. That is there exist two disjoint open sets U and V such that X belongs to U and C is subset of V. So it's like this. X is a Hausdorff space. C, it's a compact subset of X. X is a point in X in topological space X such that X is not in C. Then we need to show that there exist two disjoint open sets. One contains the point X and the second contains this compact set C. So there are two open sets, disjoint open sets. U, which contains the point X, and second is V, which contains the compact set C. So that's what we have to prove. So let's prove this theorem. Let Y belongs to C, be any point of C. Then Y is not equal to C. Y is not equal to X, sorry. Y is not equal to X. Because X is not in C. X is not in C. So that means X and Y are distinct points of Hausdorff space. So therefore, by definition, there exist two disjoint open sets, say U and V, such that U contains Y and V contains X. Since these two disjoint open sets, they depend on Y actually, because for each Y, Y is in C here. Oh, it's in C. Y is in C. It's an element of C. X is not in C. Okay, Y is in C. So for all such points y in C, every such point is not equal to x, and for any two distinct points of x, we can find two disjoint open sets containing these 2 points. So that means these 2 open sets must depend on y, because if whenever we choose a point y in C, then y is not equal to x, and then by the property of Housdorff space, by the definition of Housdorff space, there are disjoint open sets. So these open sets must depend on y. Then by definition of Housdorff space, there exist disjoint open sets uy and vy such that x belongs to uy and y belongs to vy. Y belongs to vy. So for any y which is in C, I can find neighborhood vy which contains this point phi. Okay. Now let's take this class. So let's take this class C, which is like this vy, such that y is in C. Then there are open sets, and one can easily verify that these open sets, they cover C. Then C is subset of such a union of such open sets where y belongs to C. This can be easily verified. I will write here it. So C, what's C actually? It's union of the singleton set y, where y belongs to C, and each y is a member of vy. So that means this set, singleton set y, it is subset of the open set vy. So it will be subset of vy, where y is in C. So that means C is an open cover. This cursive C, it's an open cover of C. That's C, this one. So therefore, cursive C is an open cover of C, and C is compact. Therefore, this open cover of C can be reduced to a finite subcover. And can be reduced to a finite subcover. So what's the reason? Because C is compact. Every open cover of X can be reduced to a finite. Every open cover of C can be reduced to a finite subcover as C is compact. So the reason for this is as this C is compact, as C is compact. So let's take the finite members from this cursive C. So let's take since this cover of C can be reduced to a finite subcover, so we can find finite members from cursive C which covers C. So let's let V1, V2 up to Vn, they belongs to C, such that C is subset of union I runs from 1 to n Vi. vi. But the open sets Vy, Uy, they exist in pairs. So for these, for Vy, for this open set Vy, we have an open set Uy. They exist in pairs and they are disjoint. So it means for such open sets V1, V2, Vn, we have n open sets U1, U2, Un, such that these n open sets contains the point x. So that let U1, U2, so on, Un be open sets. Corresponding to these open sets, corresponding to V1, to so on up to Vn, such that x belongs to Ui 1 less or equal to I less or equal to n. So let V be the union. So union I runs from 1 to n. Then V is open because it is the finite union of open set. It's open because it's the union of open sets. Because union of open sets is again an open set. And let's take this U, which is equal to intersection Ui. I runs from 1 to n. It's an open set. V and U are open sets, because the finite intersection of open sets is again an open set. So here we are actually using the property of compact space, because C is compact, so it can be reduced. It can be covered by finite open sets, say U, V1, V2 up to Vn, and these are the corresponding open sets U1, U2, Un, such that x belongs to Ui. And here the intersection of open sets is again finite intersection of open sets is again an open set. Then this VC, it's subset of the union Vi, so it is subset of V, and x belongs to each Ui, so that means x belongs to U, where U such that this, and they are also disjoint with each, they are disjoint, V1, U1, they are disjoint sets, V2, U2, and so here I want to mention it such that x belongs to Ui 1 less or equal to I less or equal to n, and they are disjoint is phi for I runs from 1 to up to n. So where these sets V intersection U, it's the phi set, because each V1 is disjoint from U1. So you can easily verify this. It's a phi set. For suppose it's not disjoint, these two sets are not disjoint. So for if, so you can easily verify it actually. So let me show it here. So that let's say for if x belongs to this intersection V intersection U, then x belongs to V and x belongs to U. So therefore, since x is in V and V is the union, so that means x belongs to Vi naught for some I naught with 1 less or equal to I naught less or equal to n. And here x belongs to U and U is the intersection of Ui, so it means that x belongs to Ui for all I 1 less or equal to I less or equal to n. So in particular, x also belongs to Ui naught because it is true for each I, and I naught lies between 1 and n, so that means x also belongs to Ui naught. So this implies x belongs to Vi naught and x belongs to Ui naught, so which implies Vi naught intersection Ui naught is not the phi set, which is a contradiction, because here Vi intersection Ui, they are disjoint sets, so a contradiction is required. A contradiction. prediction as required. As required. So this proves the theorem completely, because in this theorem we need to prove that we have to prove that for any point x which is not in the compact set C, these x and C can be separated by disjoint open sets, and here we have these disjoint open sets V and U, C substuff V, x belongs to U. So x and C, they are separated by disjoint open sets. So now next we prove very important property of Housdorff space. In the next theorem we will show that every compact subset of Housdorff space is closed. That's very important property. In general it's not true. We give some examples of topological space in which compact space need not be closed. But if the topological space is Housdorff space, then every compact subset of that topological space which is Housdorff is always closed. That's the next theorem.